So I'm going to introduce to you my problematic, and I will define some terms. I will present the material and method that we use to answer the problematic. I will present some experimental results, then discuss whether our solution fit well the problematic, and then give conclusion in some future work. So for several missions, unmanned ground vehicle need to go faster. And when they encounter obstacles that have high height, they could tip over. When they roll in structured environments and they encounter obstacles with sufficient slope, the reaction force created has two components, horizontal and vertical. And this situation higher the risk of tipping over. So previous work shows that for different vehicle speed and obstacle heights, it exists a boundary above which the vehicle are more likely to tip over. And the solution that we propose here is a 2 degrees of freedom suspension that could damp both components of the reaction force. So we equipped a small scale vehicle with our suspension, which called SUPS 4D, that has 4 degrees of freedom. It means 4 motion possible for the wheel with in relation to the chassis. So 2 translation, horizontal translation along the x-axis and vertical translation along the z-axis that correspond to the 2 degrees of freedom of damping, and 2 rotation around the y-axis and around the z-axis. And we're going to compare this situation, this case, SUPS 4D, with the case where we replace the horizontal suspension by an aluminum rod, so that the wheel will have only 1 degree of freedom of damping. And we call this case SUPS 3D. So for the rest of my work, I will present the comparison of those 2 cases in 2 dimensions. So we use a geometric modeling, and we can see on the picture A the modeling of the suspension in 2 dimensions. So the red limb corresponds to the vertical suspension, and the blue corresponds to the horizontal one. As we can see, the wheel has the possibility to go backward and upwards. This 2D geometric modeling enables us to determine the workspace of the mechanism, which corresponds to the intersection of 4 circles of radius, the minimum and the maximum length of the horizontal and the vertical suspension. So the workspace in 2 dimensions of our mechanism is the brown area depicted in the picture B. So this workspace enables the wheel to have 2 motion in the case of the 2 degrees of freedom suspension: horizontal delta X and vertical delta Z. In the case of SUPS 3D, the case of 1 degree of freedom suspension, we have only, since the horizontal suspension is blocked, we have only the vertical motion possible, so the delta Z motion. For the kinematic analysis, since our vehicle at the time wasn't equipped with sensor, we decided to capture the obstacle crossing with a high-speed camera for different speeds, for different vehicle speeds, and the same obstacle height. So I'm going to show you a little video of that. And then we stuck on the vehicle some targets so that we could follow those targets image by image. So as you can see, the vehicle crossed the obstacle. And those targets, the 2Z coordinate of those targets are measured, and then they are filtered, and we compute some kinematic metrics that are linked to the chassis, such as the linear speed of the chassis, the deceleration, the kinetic energy, the potential energy and the pitch rate. So for the result that I'm going to present to you, all the orange curve correspond to the 2 degree of freedom suspension, and the green curve correspond to the 1 degree of freedom suspension. We capture the obstacle crossing between 0 and a time where the vehicle is still in ballistic phase, so between 0 and 0.16. And the first dots on each curve correspond to the start of the collision phase, and the second dot correspond to the end of the collision phase. So let's look at the linear speed on the picture A. We observe that the relative speed loss in the case of the 2 degree of freedom suspension is twice lower. And for the case of the pitch rates on the picture B, both cases start at 0. And for the 1 degree of freedom suspension, we observe that the pitch rate decrease is negative and decrease till 40 milliseconds, and then increase and become positive till the end of the collision phase. In the case of the 2 degree of freedom suspension, the curve orange on the picture B, it starts at 0 and remain positive till the end of the collision phase. We define the collision phase at the time between T1 and T2. So as we can see, the collision phase duration for the 2 degree of freedom suspension is 3 times higher. We notice that for the pitch rate, at the end of the pitch rate for both suspension, we notice that the pitch rate for the case of 2 degree of freedom suspension is higher, as we can see on the picture B. For the relative kinetic energy, so the kinetic energy on the picture B, we observe that the kinetic energy lost during the crossing is 3 times lower in the case of the 2 degree of freedom suspension. And for the potential energy at the end of the collision phase, it's higher for the 2 degree of freedom suspension, as we can see on the picture B. So in this table, I compute the different metric between the collision phase, so between the start and the end of the collision phase. And since even if the initial speed of the vehicle is it's a little bit higher for the case of the 2 degree of freedom suspension, we observe that the collision duration, so the time contact between the wheel and the obstacle in the case of the 2 degree of freedom suspension is 3 times higher. So it means that the vehicle will have a lot of time to climb over the obstacle. The chassis deceleration is 2 times lower, so the vehicle won't feel the same way the impact of the crossing in the case of the 2 degree of freedom suspension. The relative speed loss is 2 times lower. It means that the vehicle conserves better its speed during the crossing. The relative kinetic energy is 3 times lower. It means that it conserves better its kinetic energy while it's crossing the obstacle. And then for the 2 last parameters, the potential energy and the pitch rate, those are more related to the ballistic phase. So the pitch rate will give an information about the height of the vehicle in the ballistic phase, the maximum height reached. And the pitch rate is more interesting when we want to control the attitude of the vehicle. So as a conclusion, we can say that the suspension with 2 degree of freedom of damping enable the chassis to have lower deceleration during the crossing. It enables the chassis to lose less speed during the crossing, less kinetic energy. So it did not pitch down, but rather pitch up, which make it easy to cross any obstacle at high speed. And it's improve the global safety of the vehicle, since it reduced the risk of tipping over. So as a future work, we're going to control the suspension parameter in order to adapt for different speeds, different vertical speed and different obstacle heights, the crossing, and to control the vehicle attitude in ballistic phase. Thank you for your attention. And I'm going to show you another video. Yes. Thank you. So thank you for your attention.
So do anyone have any question for Denis? Quick question? No? So Denis, how much is the size of your vehicle, and can it be escalated so to a larger vehicle? For example, a suspension system?
Yeah, my vehicle is like 50 centimeter longer and 40 centimeter width. And we try to prototype something. First, we try to put, we are trying to prototype something on a small scale, and then there is a possibility to use it on an agricultural vehicle. So yeah, so for now, yeah, it's a prototype, and after, yeah. Thank you very much. You're welcome.